Question 11 from the 2025 National Physics Examination from the SQA. This is from paper 1. A technician uses an oscilloscope to test 3 different power supplies. The diagrams represent the traces seen on the screen of the oscilloscope. You're shown trace X, trace Y and trace Z. And you've got to determine which of these are a DC and which of these are AC. So if we look at my simulation here, we'll go and look at this one here. We can see that we've got the oscilloscope, we've got an AC power supply and we've got a DC power supply. Well, first of all, we put onto a DC power supply. You can see we're going to get a straight line across. The trace is going to be a straight line. That's DC. Even if we change the polarity of the battery, it just means the line moves down and we get that kind of trace. So any straight line above the line or below the line is DC. AC, on the other hand, is this pattern here. We can see that the current is changing directions. It rises to a maximum and then falls down to 0, then changes in other direction. So for DC, we're looking for 2 straight lines, and for AC, we're looking for the famous sine curve like that. So let's go back to our paper and decide which one we're going to have. So you can see from our diagrams here, we have the following. That is going to be DC, this is going to be DC, and that's going to be AC. So we're looking for DC, DC and AC, and our response is going to be E. Question 12. An electric field exists around 2 point charges Q and R. The diagram shows the path taken by a charged particle as it travels through the field. The motion of the particle is shown there. You can see the particle is coming along this way and then sweeps around like that. Now it says which row in the table identifies the charge on the particle, the charge on Q and the charge on R. Well, quite simply, if it's going to be a positive charge here, it's going to be attracted to a negative charge here and it moves towards here, and of course it's going to be attracted to a negative charge here as well and then sweeps away. So the answer we're looking for is positive, negative and negative, and our response is A. And just a little bit addition to this question, this is not really a good question in the sense that the path taken by the charged particle is more complicated than that path there, but I'll leave it at that, and you can go into any simulation site where you have charged particles and you can see what I mean. But anyway, for the National 5, the response is A. Question 13. A circuit is set up as shown. The reading on the voltmeter is 3 volts and we are asked to determine the value of resistance R. There's only one way to do this, and that's to do the Sudoku method, and that's to give labels to each of the components. We'll start with this resistor here and we'll give the components the component label V, I and R. And this one down here, we'll give the labels V, I and R as well, because that's all we really need to know in this question. Now we've got to fill in all the data we know. It says the reading on the voltmeter is 3 volts, so right away I can put down there 3 volts. And resistance R, we know is going to be 240 ohms. We can fill that in there, and notice we haven't got the current. Now up here we know that since we've got a 12 volt supply and we'll put 3 volts across this resistor here, then by a voltage divider circuit there must be 9 volts across this resistor here, so we've got 9 volts there. We don't know the current, we don't know the resistance, but we can find the current in this part here because we've just got one missing. So we go and we say that V equals IR for this part of the circuit, and therefore the current flowing through that resistor, which will also through the resistor R, is V divided by the resistance, which is going to give us the following. It's going to give us 3 divided by 240, and we work the current out and the current becomes equal to 0.0125 amps. So we've now got the current which is flowing through that resistor, and that'll be exactly the same current as flowing through this resistor, so we can put that in as well at 0.0125, 0.0125. And look again, we've got to find only one thing out of 3, and that's the resistance. So we go to our equation, we know that resistance is equal to voltage divided by current. We know the voltage across this resistor is going to be 9 volts, and we know the current going through it is the same as the current going through here, 0.0125. So if we do the calculation for that, we get a value of equal to 720 ohms. So we now have completed the whole diagram, 720 ohms. We know everything about that circuit. So our response to this one is going to be D. The resistor has a value of 720 ohms. Question 14. Three resistors are connected as shown, and we're asked to find the total resistance between X and Y. This is also a kind of difficult problem because we find it very difficult to see which part is the parallel combination. So we start here at X, and electricity, the electric current, will flow through this resistor here, and when it gets to this point here, it's going to split up, and it splits up going that way and going this way. So this part of the circuit, the two 12 ohm resistors are connected in parallel. So that's the parallel part of the circuit which we have to find the combined resistance of. Now another way of thinking about that circuit is to stretch this point X and stretch it up the way, and we get this part of the circuit here like that. That's the X, going through 12 ohms, going through 12 ohms, and it gets to the part here where the current has to split. So that's the parallel part. So what in essence we have here is the following. We have this type of circuit. We have got X, we have got our 12 ohm resistor down here like that. I'll draw it in, 12 ohms. And we have got our parallel combination which we can replace with an equivalent resistor. And if you've got two 12 ohm resistors in parallel, the combined resistance is going to be half of that, which is going to be 6. So we have this setup. We have X and Y, we have a 12 ohm and a 6 ohm resistor in series now, and therefore the total resistance must be equal to 18 ohms. So our response for this question is 18, is going to be D. Question 15. A circuit is set up as shown. We have a battery of 12 volts, we've got an ammeter, we've got a 16 ohm resistor, and we've got a lamp. It says the reading on the ammeter is 0.50 amps, and the resistance of the lamp is 8 ohms, and we're asked to find the power dissipated in the lamp. The power dissipated is really the power which has been lost in the lamp, been changed into light and heat. Now, like all these electric circuits, we put down our lists, and our list is the following. We can look at the 16 ohm resistor and put down V, I and R, and we also can put down the power as well. And for the lamp, we can do the same thing, V, I and R, and we can put down the power as well and fill in as much as we know. Well, we're concentrating the lamp first of all. We look at this lamp here. We don't really know the voltage of the lamp, but we have to work that out. We know the current going through the lamp is 0.50 amps because that's the current going through the ammeter, which will go through the resistor, which will go through the lamp. We don't know the resistance of the lamp. Well, we do. It's going to be 8 ohms. We can put that in there like that. So we've got 2, and we have to find the power, and we go and look up our relationship sheet, and we know that the power can be written as I squared times R. We know the current going through the lamp, and we know its resistance, we can find its power. And we do know the current going through it, 0.5 amps. We do know the resistance of it, so we just need to plug in the values. Power equals I squared, which is 0.5 that squared, times the resistance, which is going to give you 8 ohms. And if we do that in our calculator, we end up with a value of 2 watts. That is going to be the power dissipated in the lamp, and therefore our response is going to be A for question 15.